Hello everyone. My name is Professor Anil Fernando from University of Scotland from the Computer Science Department. So today I'm going to talk about semantic communication based video coding using temporal prediction of deep neural network parameters. So to start with the presentation, I just want to give you a brief introduction to my research team here in Scotland. So I have about 20 plus researchers working on different aspects of vision processing and communication and AI. So a lot of people are working on semantic communications, which involve image and video compression and transmission, noise modeling in semantic communication, quality metrics for media applications in semantic communication applications, machine-to-machine and 6G media applications, again based on semantic communications. Apart from that, so some people are also working on video coding and communications, uh, mainly traditional statistical signal processing based video coding and communications. And moreover, most of the people are now working on machine learning for different aspects like livestock farming, human health, animal health, insurance and finance sector, and much more applications from machine learning. And finally, some people are also working on personalized future advertising in linear and nonlinear media applications. And this is a snapshot of how the research is being carried out at the moment. Most of the people are working on media communications, mainly vision communication, which involves semantic communication, 360 video, 360 viewport prediction and coding, semantic feature extraction and masking, semantic noise modeling, secure semantic communication, programmatic advertising in video, and so on. And some other people are also working on next generation networks, which involve compression and transmission of IoT applications, quantum communication, neuromorphic coding, mainly for vision applications again. Other than that, some other people are working on digital health, finance, and energy management. To start this presentation, so I'll just give you a brief introduction to semantic communication, people who do not know anything about semantic communication. So before we talk about semantic communication, let's understand how the present communication system works. So we have a source which generates some of the information. The source can be a microphone or video camera, which generates some audio video visual content. And then we have a source encoder to exploit the correlation between the information to reduce the bit rate or the bandwidth. And then source encoder gives output to the channel encoder. The function of the channel encoder is to protect the data during the transmission because the transmission medium will add some noise to the signal. So the purpose of the channel encoding is to protect this data against this noise. And then we have a digital modulator to modulate the signal. And after the modulation, the signal is feed into the channel. Channel is obviously a noisy environment which will add some noise to the signal. And then at the receiving side, we will do the inverse operation, demodulator to demodulate the signal, and then channel decoder to remove the noise as much as possible, which was added during the transmission, and then source decoder to decode the source encoded information, and then finally put into the display or the destination device. So that's the classical communication system currently people have been using for information transmission. So the problem of communication has been defined in 1949, about 75 years ago, by a scientist called Shannon. So he told us like we have the communication can be divided into three segments: technical problem, which accurately transmit the information from sender to the receiver; semantic problem, which is defined as the interpretation of the meaning by the receiver as compared with the intended meaning of the sender; and then finally the last layer is the effectiveness problem, which is the success with which the meaning conveyed to the receiver leads to a desired conduct. So far people we have been using the technical layer. That's what I explained before. Now we move to the semantic problem. We'll understand why semantic communication is needed because of the saturation of the channel bandwidth we are experiencing today, especially the wireless communication. The bandwidth is getting saturated now, so we can't increase the bandwidth anymore. So then the maximum amount of information which can carry by a channel is defined by the channel, which I'll explain it a bit later. So semantic communication attempts to achieve effectiveness of communication by solving the semantic problem, even when the technical problem is not fully resolved using shared context between the sender and the receiver. So the concept was first introduced in 1949 by Shannon and Weaver, but no effective method for implementation for many decades, mainly due to the computational complexity required for the machines to understand the semantics of the information. So advances in machine learning and wide availability of computers capable of training artificial neural networks brought in a breakthrough in late 2010s. Since 2020, so there is a resurgence of interest as evidenced by Google tells. However, much work is needed to realize this potential to the expected level. So based on that, this is how the semantic communication system is defined. Uh, we have the source, and then we have the semantic encoder, which extracts the semantic meaning of the information, and channel encoder, modulator, channel, technical noise, demodulator, channel decoder, semantic decoder, destination. So this path is almost like same as the classical communication system. Apart from the source encoder is replaced by a semantic encoder. So the purpose of the semantic encoder is to extract the meaning of the information, and then the context information is shared between the transmitter and the receiver using a set of known information. We define them as like a shared knowledge between the transmitter and the receiver. So then the context information cannot be 100% defined by the transmitter, and therefore the context information cannot be transmitted directly from the transmitter to receiver depending on the application. So therefore, there is always some kind of noise embedded to the information, which is defined as the semantic noise. So apart from the technical noise, now we have a new term, which is the semantic noise. Then the dependency of the semantic noise depends on how well the source and the destination exchange the shared knowledge. Depending on the shared knowledge, semantic noise can be varied for different applications. So this is the highlighted box that we have been focusing for 2 years now within my research group in defining the semantic communication system. So we have the source, semantic encoder, and then we have, like I explained before, the context is derived. And then based on the context, we have a semantic noise apart from the technical noise. So the objective is modeling and improving performance of the semantic channel such that the volume of the data needs to be transmitted from the source to the destination will be minimized. So what are the applications of semantic communication? Mainly, like I told you before, even though the channel saturation is happening, we have different applications which needs very high bandwidth. For example, super high resolution of video, which is talking about 16 K spatial resolution at 300 frames a second, which will generate a massive data rate even after the compression. So that kind of data rate cannot be accommodated supported by the existing or emerging wireless channels. So omnidirectional video communication is another aspect of video which we consume like 360 video at receiving points. So extended reality is also gaining a huge attention nowadays for different virtual production and so on. That will also deal with very high data rates. Region of interest-based media coding and communication, scalable media coding and communication, Internet of Things. This is another demanding area, especially for low bit rate, low energy applications. we call it as video or video of Internet of Things, VIoT, and machine-to-machine communication, which also involves a lot of data rates between machines and narrowband video sensing. So all these applications demands very critical system resources which cannot be supported by the existing uh, infrastructure, mainly for wireless applications. So to replace these traditional challenges, semantic communication can peep into these domains and then provide some sensible solutions. So introduction to this particular speech. So this is all about, again, video coding, an essential capability of gaming entertainment media ecosystem. Emerging applications challenge conventional techniques. So deep neural network provide an alternative, but transmitting the DNN parameters or deep neural network parameters between videos transmitter and receiver is a challenge. So to resolve that, some people have come up with some kind of a compression mechanism. We call it as neural network compression to compress the network parameters, but this requires a very high bit rate, especially for video applications. So this is not going to be the best solution that we can think of. So as the first step, we propose a semantic communication-based alternative solution in this talk. The key contribution that I'm talking today is to use of DNA-based semantic communication system for video coding and transmission applications, introducing a technique for temporal prediction of DNA parameter in video applications, demonstrating the effective combination of DNA and neural network compression for video coding and transmission. So remember that this is just the first attempt of solving this problem of DNA-based video coding using semantic communications and how neural network compression can be used to reduce the data rate. So let's talk about briefly about DNA-based video coding. So DNA inherently good at compressing complex data such as video. DNA application in video coding is now widely researched, but the key challenges still people have not resolved is like time taken and accuracy of DNA training, sharing trained neural networks between transmitter and the receiver, handling residuals of predicted frames for better human perception. Uh, you should know like DNN is been well researched at the moment for video coding application, but sending these network parameters from transmitter to receiver is the main challenge. Apart from that, also DNN will have residuals because the prediction cannot be 100% accurate. So these residuals is another big problem, how to minimize these residuals and how to transmit them from place A to the place B. So DNN's enable implementation of semantic communication is the core technology that we are proposing here. So this is the same network that I had talked before, and we are talking about the semantic encoder and the decoder. So let's talk about neural network compression. Basically, DNA-based video codec creates significant frame residuals. Overfitted DNA trained with very small batches reduces this, but requires more frequent parameter updates between the transmitter and the receiver. Neural network compression provides a method to reduce the bandwidth required for this, but that's again very high compared to the raw data that we are transmitting from A to B. Multiple techniques are proposed to achieve this. Neural network encoder decoder software is an optimized implementation of a neural network compression used as a benchmark for today's state-of-the-art video coding using DNN. And this is what we proposed here. What we do is like we send some of the shared knowledge between the transmitter and the receiver using some of the key frames. We define them as HEIF encoded frames between the transmitter and the receiver. And then we use an autoencoder to transmit the key intra frames, the frames in between key frames as a way of transmitting the information. And obviously, this DNN is autoencoder is kind of a DNN architecture that we can use between the transmitter and the receiver. So once the DNA-based vectors are transmitted between the transmitter and the receiver, so we have compressed the residual using the neural network compression algorithm that we talked about before, and then send it to the receiver for regenerating the residual. And with the autoencoder decoder, and we combine the residual and the latent vectors to regenerate the frames. So that's the concept of the technology that we are proposing here. So what we do is we use the DNA characteristics with trained parameters. So we have basically based on the biases in the neural network. So what we do is using the frame interpolation, like the frame correlation between the frames in the video. We have researched how weights and biases are correlated against the frames, and we found that weights and biases are also have a similar performance like the temporal correlation between the frames. So what we do is we will predict the frame, the weights and the biases between the frames. For example, when the frame 1 information is sent to the receiver, we try to predict the frame 2 parameters from the frame 1 and send the residuals to the receiver using the neural network compression architecture. So we have tested this for different sort of videos which has different structural and temporal information ranging from very low to very high. And then this is the neural network model or autoencoder model that we use for this experiment. And these are the summary of the results together with the state-of-the-art NNC compression. The red one shows the performance of the proposed one, where the blue one presents the neural network compression state-of-the-art networks. So you can see there's a massive gain between the proposed and the state-of-the-art. The bit rate is significantly reduced, whereas the quality has also been increased across all the videos we tested. And remember that this is just the first attempt of predicting the neural network parameters in the temporal domain using temporal correlations. And the conclusions of the next step is while proposed systems adds complexity, it has a significant rate distortion performance increase again compared to the NNC codec alone. Both proposed and NNC codecs still have significant Just to conclude the presentation, we are open for any collaborations within this domain. Anybody who is working on AI or machine learning or signal processing or communication, video coding, or anything related to the algorithmic design or video codecs or communication, they are invited for collaborations with us. So we have like about 20 researchers working on different aspects of this topic, and we are cordially invited for working with them for future collaborations. If anybody is interested about what we are doing, and here is my contact details. The email address is given here. The URL is also given here for you to find more information and to be in touch with us. So please do in touch with us for any collaborations, possible collaborations. You are more than welcome to join with us and work with us in this interesting topic. Thank you very much.